Okay, it's a great pleasure for me to introduce Ulrik Enstad from the University of Stockholm. He's going to talk about frames in the orbit of group representations via von Neumann algebras. So thank you very much for accepting to participate in our seminar, and it's all yours. I invite everybody to close the video.
Thank you so much for the invitation to speak here. It's a pleasure. And also, if you have any questions along the way, feel free to interrupt. So I'm going to talk about a topic which is a bit, I guess, at the crossroads between more harmonic analysis, frame theory, and operator algebras. So let me set the stage for the problems that I want to discuss. So throughout, I'm going to fix a group representation of a locally compact group G, which is going to be irreducible, so irreducible unitary group representation. And I will denote the representation space by H pi, so it's a Hilbert space. And in this setting, we know that since this representation is irreducible, if we take any non-zero vector and we apply pi of x to this vector as x ranges through the whole group G, then this is going to be a complete system in the Hilbert space, simply because the closed linear span of this family is a G invariant non-trivial subspace, so it has to be the whole Hilbert space. But what we're going to do instead is we're going to replace G by some discrete subset of G. We're going to ask the same question. So when is this family? So we apply pi of gamma to this vector eta, but now we let gamma run through this discrete subset gamma of G, and we ask when is this family complete in the Hilbert space? And actually, more generally, we're going to look at the following. So already now, I'm going to restrict this discrete subset to be a lattice, so a discrete subgroup of G with finite covolume. And then on one hand, we can look at when this family pi of gamma eta, which we call a lattice orbit of pi. So when does this family have suitable spanning properties? Which, I mean, spanning property is of course a vague term, but completeness is sort of the weakest such term, and we're going to look at the frame property, which many of you might know is a stronger property. And on the other hand, when does this family have suitable linear independence properties? So this sort of thing I'm going to discuss. And already at this point, one might say that there's a certain intuition, namely that for this family to have a spanning property, this lattice orbit indexed by gamma, for this family to have sufficient spanning properties, it makes sense that the lattice should be sufficiently dense, so the points should sort of be sufficiently dense in the group. While on the other hand, for this family to be linear independent, the lattice should be sufficiently sparse. And as we'll see, this intuition will turn into a concrete theorem with some extra assumptions. Right, so I use the terms spanning and linear independence, which are rather vague in infinite dimensions. But there are some concrete notions that I want to introduce. And I think a good way to motivate these notions is to first look at the defining properties of an orthonormal basis. Right, so if you take an orthonormal basis, it's characterized by two properties, namely Parsifal's identity, which is a spanning property, and orthonormality, which is a linear independence property. And I've written orthonormality here in a bit non-standard way, but it is really equivalent. And the idea now is if we take Parsifal's identity and we deform it a little bit, so instead of having this equality on the nose, we only have it up to two different but uniform multiples of xi squared, the norm of xi squared, then we call the family a frame. So it's just a weakening of Parsifal's identity. And frames are very nice, still very nice spanning properties, spanning families in the Hilbert space. And if we do the same thing with an orthonormal set, then we get the notion of a resequence. So we just deform this equality so that we get the corresponding double inequality. And then a Rees basis is then a sequence which is both the frame and the resequence, which then is a generalization of an orthonormal basis. And so what I'm going to talk about is the existence of these lattice orbits that satisfy the frame property, the resequence property, and the Rees basis property. Right, so there's a motivating example that I want to quickly discuss. So if you let G be R to the 2D, which we can use R to the D times R to the D, then there's a certain important representation of this group, namely the Heisenberg representation, which acts or which is realized on L2 of RD. And it's given as follows. So pi of x omega, here x and omega are two elements in R to the D. This tuple acts on the function by shifting it in time, so to say, by the first coordinate x, and then modulating using the second coordinate. So this operation is called a time frequency shift. And something to note about this this representation is that it's actually not a representation on the nose, but it's rather a projective representation, which means that when we compose two such time frequency shifts, in this case, we don't get exactly so the representation corresponding to the group law, but we have this phase factor in the front. And this fits into the general framework of a projective representation, where there's a certain function, namely an associated 2 cocycle, which is in the front here, which satisfies it has to satisfy some properties from this projective representation composition law. And I'm going to allow pi to be projective with respect to some cocycle throughout the talk to cover interesting or important examples such as the Heisenberg representation. But in this context, if we now look at these lattice orbits, so we take some lattice in the group, namely R to the 2D, apply pi gamma to some fixed function eta in L2 of RD, then these lattice orbits are known as Gabor systems, and they have been, and they are still extensively studied in time frequency analysis. So Gabor systems are really a special case of this more general framework. And picking other groups and other representations leads, for instance, to wavelet theory. So let's go back to the general setting. So I'm going to put some assumptions. So we're going to assume that G is unimodular and second countable. And now pi is allowed to be sigma projective with respect to some cocycle. But I'm going to assume that pi is square-integrable, which means that we can find at least one non-zero matrix coefficient of pi, which is in L2 of G. So here we integrate with respect to some R measure. And under the present assumptions, square integrability actually implies that all matrix coefficients of pi are going to be square integrable. And in fact, we have these orthogonality relations. So we take the L2 inner product of two different matrix coefficients with respect to pi. Then this just reduces to taking inner products in the Hilbert space H pi. But then we have this factor in the front, d pi inverse. And this number d pi is called the formal dimension of the representation. Right, so we're going to assume that pi is of this type. And then there's a necessary condition, for the existence of these lattice orbit frames and V-sequences, which is called the density theorem. In our setting, it states the following. So we have a projective unitary representation of G as before. We take a lattice gamma in G, and then the following hold for any vector eta in H pi. So if this lattice orbit family is a frame, then the number d pi times the co-volume of lattice has to be less than or equal to 1. And then dually, if this lattice orbit is a V-sequence, then the number has to be bigger than or equal to 1. And if these two are combined, one sees that in order to have the existence of a V-spaces, it forces this number to be equal to. And this formalizes the intuition I talked about earlier, because the smaller the co-volume of a lattice is, the more densely packed together the points of the lattice is. So this really tells us that there's a certain critical density, which the co-volume of the lattice has to be below in order for frames to exist over this lattice. And then one has the opposite situation with V-sequences. So let me talk a bit about the background of this theorem. It has a long history for Gabor frames. So in other words, with a projective Heisenberg representation with many different, so I mean, it has been proved in increasing generality over the years. And the version I've stated here, I've credited to José Luis Romero and Jordi van Velthoven, who proved this in a preprint not so long ago. Right. So, but what I want to talk about now is, what about the converse of this theorem? So we know that in order for that to be a frame, this number here has to be less than or equal to 1. But what about the opposite? So in other words, if we have a lattice for which this number is less than or equal to 1, can we then deduce that there exists some vector in H pi for which this lattice orbit is a frame? And then one can ask the corresponding or the analogous questions for Rees sequences and Rees spaces. So if one has a lattice for which the number is bigger than or equal to 1, can we then find a Rees sequence of this form? And then if the number is equal to 1, can we find the Rees spaces? And the answer is that it depends on the representation and the group. So for instance, in the case of Gabor frames, the answer turns out to be yes to all of the questions above. And this was proved, or the first part and the third part in the case of Gabor frames was proved by Bekka using phenomenal algebra techniques. But I'm not aware of this second statement having appeared explicitly before. So, but I'm going to show. I want to show you how this can be deduced as well. The second statement, also using phenomenal algebra techniques. Right, so that's the case. So as I mentioned, in the case of Gabor frames, we can reverse all these implications, but the answer in general is that it's not possible. So sometimes one can have this inequality without having the existence of a frame, for instance. And we'll see sort of why that can happen later on. So the idea now was that I wanted to show how this problem, this existence problem, can be approached using phenomenal algebras by sort of gradually shifting away from frames and degree sequences and into more representation theoretic and phenomenal algebraic stuff. And so the first thing one has to do is to reformulate these existence properties. So in order to do this, there's a certain canonical representation that we need. So here, gamma is just some discrete group. And we also fix a 2 cocycle sigma on gamma. And then the sigma twisted left regular representation, which we denote by lambda sigma, is the sigma projective representation realized on L2 of gamma, which is given by this formula. And so you see that if you just omit this factor with sigma, then it's just the usual left regular representation. But adding this sigma factor makes it the projective representation rather than ordinary representation. Right, and then it turns out that this existence of a frame property that we're dealing with, so the existence of an eta in H pi such that the associated lattice orbit is a frame, this is equivalent to the restriction of pi to gamma being a sub-representation of this sigma twisted left regular representation. And then if we instead ask for the existence of a resequence of the same form, then this is equivalent to having a sub-representation going the other way around. And this is quite elementary, actually. So if we have a frame of this form, then there's this certain associated coefficient or analysis operator, which takes you from the representation space and into the sequence space. And it just maps a vector psi to the sequence of inner products between, or where psi, we would take this inner product of psi with just the frame vectors. And this double inequality defining a frame, so this A and B double inequality, can now be just, it can be recast as by saying that this operator here, C, is bounded above, which is the upper frame inequality, bounded below, which is the lower frame inequality. And one also checks that it actually intertwines these two representations. So this shows that the restriction of pi to gamma is a sub-representation of lambda sigma. And then what about the other way? Well, if we assume that we have sub-representations, then there's this canonical orthonormal basis, right, for L2 of gamma, which is just the vector delta E, where we apply the left regular representation. And we can just project this basis more or less down to H pi, and then we get a frame in H pi. So this gives us a way of moving away from these existence of frames and resequence properties and more into the territory of representation theory. And so the idea now is that we want to extend what happens here linearly to get Hilbert modules over phenomenal algebras. So let me begin by just giving the necessary prerequisites on phenomenal algebras. So, well, first of all, a phenomenal algebra A acting on the Hilbert space H is a unital subalgebra A of bounded linear operators on H, which is closed under taking adjoints of operators and also closed under taking limits in the weak operator topology. And then we're only going to be looking at finite phenomenal algebras. And these phenomenal algebras are characterized by the existence of a unique so-called center value trace or faithful normal center value trace, which is a map that goes from M and not into the complex numbers as with the usual trace, but into the center of M. But it has the similar trace-like properties. So the trace of AB is the trace of BA and so on. And yeah, and then there's the basic theory of projections in phenomenal algebras. So a projection in a phenomenal algebra is it's a self-adjoint idempotent element. We call two such projections P and Q equivalent if we can find a U, so a partial isometry U in the phenomenal algebra, such that P is the initial projection of this partial isometry, while Q is the final projection. And then we say that P is sub-equivalent to Q if P is equivalent to some sub-projection of Q. And the thing about this center value trace is that it detects equivalence and sub-equivalence of projections. And this is sort of the theoretical cornerstone of the theorems that I will present later. It's really what makes everything work. So we have that P is sub-equivalent to Q if and only if the trace of P is less than or equal to the trace of Q. So in particular, it's the implication from right to left, which is the most non-trivial here. So going from something tracial to something about comparing projections. And similarly, we have that P is equivalent to Q if and only if the trace of P is equal to the trace of Q. Right, so this is going to be used, but we sort of need to lift this up to the level of modules. So let us define what a Hilbert module is over a phenomenal algebra. So a Hilbert module over M, that's just a Hilbert space H on which the phenomenal algebra acts. So through a normal representation of M on this Hilbert space. And then under certain separability assumptions, one can actually always embed such Hilbert modules into a bigger sort of free module associated to the phenomenal algebra. And so more specifically, if we equip M with some faithful normal tracial state, tau, in the setting that we're going to see later, there's also always a canonical such trace. Right, then we have to assume that M is has a separable p-dual and H is separable. Then we can always embed H as a submodule of the GNS space associated to M and tau. And then we just tensor it with some, it's not important that it's L2 of N, it just has to be some separable infinite dimensional Hilbert space. But M acts on this space just diagonally, it just acts on this GNS space. And then as soon as you have embedded your Hilbert module into this bigger free module, then you can form the projection going from the bigger module down onto your Hilbert module, and you can essentially take the trace of this projection. And that's something we define to be the center valued von Neumann dimension of the Hilbert module. So you take the trace associated to, yes, another thing is that this projection representing your Hilbert space is now in the commutant of M on the GNS space of M, and then tensor the boundary linear operators in L2 of N. So we can think of this projection as just an infinite matrix with entries in the commutant of M. And the trace of this projection is then just defined by taking the center value trace associated to the commutant of M, applying it to the diagonal entries of this matrix, and then just summing them up like a usual matrix trace. And then sort of the beefed up version of the theorem on the last slide is an analogous theorem for Hilbert modules. So it turns out that H, a Hilbert module H, is a submodule of a Hilbert module H prime, if and only if we have this comparing of their center value dimensions, so this inequality. And then analogously, H is isomorphic to H prime, if and only if their center value dimensions agree everywhere. And these hold when these two projections are finite. Yeah, so this is going to be the key tool from operator algebras, so to say, this theorem. But let us move away from generalities to more specific things. So the finite phenomenal algebras that are interesting in this setting will be the twisted group phenomenal algebras associated to the lattice gamma. So again, now gamma is just a discrete group, and sigma is a cocycle, two cocycle on gamma. And then this twisted group phenomenal algebra is simply the phenomenal algebra generated by the image of the sigma twisted left triangle representation. So it's a von Neumann subalgebra of the bound linear operators in L2 of gamma. And if you have seen, I mean, it's if you set this co-cycle sigma to be just constantly equal to 1, then you recover the usual untwisted group von Neumann algebra. And how do these operators act? So if we have an A in this von Neumann algebra, we can describe how it acts on elements in L2 of G, L2 of gamma, by twisted convolution. So for session A, just set phi to be A applied to delta E, which will then be an element in L2 of gamma. And then the way A acts on general F in L2 of gamma is by this twisted convolution operation between phi and F. And the definition of twisted convolution is as follows. So it's just like ordinary convolution, but there's this twist impactor coming from sigma involved. And similarly, we can characterize positivity of elements in this von Neumann algebra. So the element A is positive if and only if this associated function phi is what we call sigma positive definite, which is again a sort of twisted version of the usual positive definiteness. So we require that this inequality here holds for all C1 up to Cn complex numbers and elements gamma 1 up to gamma n in the group. But again, if you just set this co-cycle factor equal to 1, you recover ordinary positive definiteness. So it's just a twisted, it's a twisted version of a well-known concept. Right, and then one can ask, what is the center value trace on this twisted group von Neumann algebra? And in order to define that, we first need the notion of a sigma regular element. So we call an element gamma in the group sigma regular if whenever another element gamma prime in the group commutes with gamma, then sigma of gamma prime is equal to sigma of gamma prime gamma. And then the center value trace of this von Neumann algebra can be given as follows. So if we take an element gamma in the group, which is sigma regular, according to the definition above, and this such that its conjugacy class is finite. So say it's equal to this, so B1 inverse gamma B1 up to Bn inverse gamma Bn. In that case, the center value trace of the element lambda sigma gamma of the group von Neumann algebra is given by this sort of averaging over the conjugacy class, but where we twist using the co-cycle. Otherwise, it's 0. And in the untwisted case, this formula is well known, but I wasn't able to find a proof of this formula in the twisted case, but the proof is similar, except there's extra work needed to keep track of all these co-cycle terms. And then, so this von Neumann algebra is a factor, so meaning that its center is trivial. This is if and only if the pair gamma sigma satisfies the so-called Kleppner's condition, which is that the only sigma regular element with finite conjugacy class is the identity. So this was proved by Kleppner back in the 60s. And as you can see here, if you set sigma to be equal to 1 again, then any element is automatically sigma regular. So then this condition is just the ICC condition, namely that any non-trivial element has infinite conjugacy class. And that's a very well-known characterization of when a group von Neumann algebra is a factor, namely that the group has to be ICC. All right. Yes, so as we saw earlier, we are interested in this restriction of pi to gamma as a representation of gamma. And this turns out to extend to give h pi the structure of a Hilbert module over this twisted group polynomial algebra. So it's just a linear extension where you extend the action of pi restricted to gamma on h pi. Yeah, and this can be proved using fundamental domains, essentially, that that we have such an extension. So this means that we can view h pi as a Hilbert module, and then what we're going to be interested in is the center value trace of this module, h pi. So we set A to be the center value trace of h pi, and then a bit similar, but also a bit different to just the case where we have elements in the group polynomial algebra itself. This center value trace is going to act via convolution with the function phi, which is just A applied to delta E. And now a fact is that since this is a lattice, this is going to give us a function, a bounded function on gamma. And then finally we can get a nicer characterization of these existence properties. So there exists a vector that such that this lattice orbit is a frame if and only if this associated function, so delta E minus the function phi above, if and only if this function is sigma positive definite, according to the definition on the previous slide. And then for the existence of resequences, we sort of get the opposite condition, that phi minus delta E should be sigma positive definite. And then the existence of respaces of this form over the fixed lattice is then equivalent to phi being equal to delta E. And how do we get this? Well, so we start by this observation that, so now I'm taking the frame equivalence, but the resequence equivalence is similar. But we start with this observation that the existence of a frame is equal to having that pi restricted to gamma is a subrepresentation of lambda sigma. But this just extends linearly to the condition that h pi is a submodule, so sub-Hilbert module of L2 of gamma. But as we saw, there was this crucial technical tool that characterizes when we have submodules, Hilbert submodules, in terms of center valued traces or center valued polynomial dimensions. So this is an equivalent to A being less than or equal to the center valued polynomial dimension of just the GNS space of gamma itself, which is just the identity operator. So we really have here that we want I minus A to be a positive operator, but then in terms of the function that this operator is given by convolving with, this function then has to be sigma positive definite. So that's really how we get from the existence of a frame or resequence or respaces to having some positive definiteness of functions. But the question still remains, how do we describe this phi? Because so far it's just phi is A applied to delta E, but we can't really do anything before we have a better description of phi. And so this is what Bekka did in the 2004 paper. He described this function phi in the case of ordinary representations. So not sigma projective, but just ordinary representations. But the assumptions are as before. We take a lattice, we fix any unit vector, and then this phi, this function phi, is given as follows. So if we have an element gamma for which the conjugacy class is finite, then phi of gamma is given by this formula. So we have the formal dimension b pi appearing here. We divide by the size of the conjugacy class, and then we integrate over this homogeneous space here. So gamma sub little gamma, that's the centralizer of the element gamma in the group gamma, which is the lattice in G. And then we integrate this matrix coefficient with respect to a suitably normalized Haar measure. Otherwise, it's just 0. And one might wonder, how does this formula look like in a twisted setting? So where we have co-cycles all the way, we have a projective representation rather than ordinary representation. And here's the answer. So if we allow pi to be sigma projective, then we need to assume that gamma is sigma regular and that the conjugacy class of gamma is finite. And in that case, formula is given by this. So it's similar as before, except we have this extra twisting term, which ultimately comes from this center value trace formula that I showed earlier. So this computation involves using the center value trace of the polynomial algebra and some other stuff. And otherwise, it's going to be 0. Right, so let's see some, still this doesn't look that good, but let us look at some consequences. So for instance, what happens when the polynomial algebra is a factor? So in other words, when we have this Kleppner's condition with respect to the cocycle. And so the first thing to note is that the value of this function phi at the identity is simply this number that we have looked at earlier. So d pi times the covolume of the lattice. And that one can see quite easily, because if you plug in the identity, then we have the conjugacy class of the identity, which is just trivial. We have the centralizer of the identity, which is the whole lattice gamma. And these cocycle terms, they vanish. Here we end up with just a norm of unit vector. So we end up integrating just a constant function over this homogeneous space, and that gives us the covolume of the lattice. So the value of this function phi at the identity is going to be simply this constant. But then what happens if we assume that our lattice satisfies Kleppner's condition? Then we get complete converse to this density theorem. So then there exists a frame of this form if and only if the number d pi times the covolume is less than or equal to 1. And for re-sequences, we have the inequality going the other way around. And then for re-spaces, we have equality. And so this was also proved by Romero and von Velthoven in their recent preprint using some more elementary methods. But we can see that it follows easily from the theorem on the last slide, simply because in this setting, this function phi is now, it's going to be 0 everywhere else except at the identity, where we know it's equal to this constant. And why is that? Well, if we go back to the definition, then this formula here only holds for sigma regular elements with finite conjugacy class. But the definition of Kleppner's condition is that there is no such element besides the identity. So this function phi just collapses to this constant here times the delta function of the identity. And so we get these complete converses. But then, of course, one doesn't want to have to assume Kleppner's condition all the time. So what about, are there other situations where we get a similar theorem but without Kleppner's condition? And it turns out that if you assume that the group is abelian, then this is always the case, at least if you additionally assume a sort of non-degeneracy condition on the cocycle. Yeah, so everything here is as before. We have a representation as before, but now we assume that G is abelian. And we assume that Kleppner's condition is satisfied, not with respect to the lattice, but with respect to the whole group. So this is much weaker. In this case, we have the same collapsing. So then phi just collapses to this constant, d pi times the covolume, times just the delta of the identity of the group. And this one can see by looking at the formula, because if we assume that we have a sigma regular element with finite conjugacy class, then of course, since we're in an abelian group, the conjugacy class is just trivial. The centralizer is all of gamma. So then what happens is that we have this y inverse gamma y term, but because of the group is abelian, the y's just cancel against each other. So we're left with this integral of a cocycle term. But this term is actually it's going to be a character in Y. And if you integrate a character over a compact abelian group, then that's going to give you 1, if and only if the character is the constant equal to 1 character and 0 otherwise. But because of Kleppner's condition, the only way for this character to be constantly equal to 1 is if gamma is already the identity of the group. So that's how we end up with this term. Right, and this applies in our motivating example, because in our motivating example, we have the group R to the 2D, which is an abelian group. So we get this consequence for Gabor frames. So, right, so we take a lattice in R to the 2D, and we take the projective Heisenberg representation, which is given by time frequency shifts. Then there exists a frame of this form, if and only if the co-volume of the lattice is less than or equal to 1. Yeah, so there's a hidden d pi here, but because of the usual normalization, this d pi becomes equal to 1. And then analogously, there exists a resequence if and only if the co-volume is bigger than or equal to 1. And there exists a respaces if and only if the co-volume is equal to 1. And as I said, Bekka proved in his paper the first and third parts here. And he did it by actually proving a slightly more general formula for representations which are square integrable only modulo the center, so not square integrable in the strict sense. And then he applied this theorem indirectly to the Heisenberg representation. But as far as I know, there's not a way to apply this square integrable modulo the center theorem to approach part 2 here. But on the other hand, having a formula for projective representations takes care of it, as we see. Right, so yeah, having gone through all those technical phenomenal algebra things, we see that in the end, we get this nice characterization of when such frames, resequences, and respaces exist in the case of Gabor frames. And there's a certain variation of the problem that I just wanted to mention in the end. So if we add some additional structure, so let's suppose that G is a Lie group, and that gamma is a lattice in G as before, and pi is a projective representation as before. Then we can look at the subset of the representation space, which we denote by h pi infinity, which consists of those vectors in h pi for which this map going from G to h pi, where we map elements of G to pi of x theta, where we require this map is smooth. And the vectors such that this map is smooth we call smooth vectors. And so, for instance, if you look at the smooth vectors in the case of the Heisenberg representation, then they become exactly the Schwartz space, which is then the subspace of L2 of R to the D, so the Schwartz space of R to the D. And one can ask the same questions, but with h pi replaced by h pi infinity. So when does there, so again, fix the lattice gamma, and then when does there exist a smooth vector such that this lattice orbit pi of gamma eta is a frame or resequence or respaces? And it turns out that this question is actually much more subtle than just asking for a vector in h pi. Namely, in many situations, there are certain no-go theorems, known as Bali-Low theorems, which assert that these inequalities that we saw earlier, they actually have to be strict. So they're not just non-strict, but they're actually strict inequalities. And again, Bali-Low theorems have a long history in the theory of Gabor frames. But one can also ask in this situation for converses, so existence. So if we have a lattice for which we have strict inequalities, can we then prove the existence of frames or resequences? And I just wanted to mention a recent result along this direction that I have together with Erik Bédos and Jordi van Velthoven, which is in a much more specific situation. So here we assume that pi is a sigma projective, so-called relative discrete series representation of a connected, simply connected nilpotent Lie group. And so this means that it comes from a square-integrable modulo the center representation, some honest representation of some nilpotent Lie group, but then you can quotient out by the center and you can obtain a projective representation of this quotient. And in this setting, if we assume that we have a lattice for which, again, the Kleppner's condition is satisfied with respect to the lattice, then we get these, we get a converse to the Bodin-Low theorem, essentially. So if d pi times the covolume of lambda is strictly less than 1, then there exists a frame generated by a smooth vector. And analogously, if we have a strict inequality going the other way, then there exists a smooth vector giving a resequence. And I don't have time to go into full detail about this, about the proof of this theorem, but let me just mention that contrary to the results with just vectors in H pi, in order to approach this problem, we found that C-star algebra techniques were preferable. So basically, we generalized some work of Rueff and Riefel, constructing some Hilbert C-star modules. And then in the end, actually getting these, going from these inequalities to some existence, actually relies on some pretty recent results from the Elliott classification program for C-star algebras. So in particular, the use of nuclear dimension and other recent notions from this program. Anyway, that's all I wanted to say. Here are some references, and thank you so much for listening.
Thank you very much. I don't know if anyone has a question or comment.
I do have just minor questions. Can you go back to the last slide, one slide back?
This one?
Yeah, this one. So yeah, I think you said that it was, well, this is new for me. I know what is a discrete zero representation. What does it mean, relative?
Yeah, so what we mean here is that relative means that it comes from an honest representation, which is square-integrable modulo the center. So it's a thing that we wanted to remove, but we weren't quite able to. So it's you want to start with an honest representation of a nilpotent Lie group, which is a square-integrable modulo the center. And then by quotienting out with the center and taking the quotient group, you then obtain a projective representation of the quotient group. And the statement is then that we want this pi to appear in that way. Essentially, it has to come from such an honest representation.
Okay, so these are particular projective representation that comes from like discrete series representation. That's how you get the cocycle, by quotient, by.
Yes.
Okay.
And whether one can obtain all projective representations in that way is something that I don't think we ever really fully settled. But yeah, if that's possible, then it would certainly make the statement of this theorem easier.
And when you use here like this, the simply connected nilpotent Lie group, so what discrete zero representation, do you use any sort of number theory? I mean, what do you use about having discrete zero representations of nilpotent Lie groups?
Right, so the nilpotent assumption is it's really important for many reasons. So one reason is that, for instance, lattices are automatically co-compact. So these things don't really seem to work if without the co-compactness. Another thing is that there's these specific mapping properties that we needed in order to construct a certain Hilbert C-star modules. So we really wanted, so you can construct sort of associated spaces of smooth sequences, and in order for these things to sort of map into each other in the right way, we constantly made use of the nilpotent assumption. So for instance, I think there's a certain intersection that we form of some function spaces, and the only way we know it's non-empty is because of nilpotency. And not to mention that in order to use these results from the classification program, they only work for finitely generated nilpotent Lie groups. So we need this lattice sitting inside G to be finitely generated nilpotent. And if G is some more general Lie group, then we can't guarantee that any longer. So
that thing again.
Right, so this what we need in the end is we need to prove that the C-star algebra, the twisted group C-star algebra of this lattice, has a finite nuclear dimension.
Yes.
And that is simply unknown beyond nilpotent discrete groups.
Oh, okay.
So that's
okay. That I know.
So this result, so the untwisted result was proved by Eckhart, McKenney, and Gillespie, and we just used their result to prove it, to extend it to the twisted setting. All that was done by them.
So this is fairly new then, because these are young people, no?
Yeah, so I guess the first paper along those lines came maybe in 2015 or something. They published some more general papers later. But actually something we're hoping to do is to generalize this to maybe to compactly generated groups of polynomial growth or something along those lines is something that might be possible, because if you take lattices, then they're going to be virtually nilpotent, and these finite nuclear dimension theorems have actually been extended to the virtually nilpotent case. So it might be possible to generalize it. Now.
Is there any other question or comment? I have a question. In this last theorem that you mentioned, the inequalities are strict. Do you have any guess of what can happen in the critical situation when the pi volume of G divided by gamma is equal to 1? Is this possible to have a vector in H infinity? Do you have a guess, or do you?
That's a very good question. So I think probably what people suspect is that it's not possible, at least in this setting. And Jordi, so van Velthoven, has proved this partially for so-called homogeneous nilpotent Lie groups, where you have some dilation structure on the Lie algebra. And for those nilpotent Lie groups, they prove that it's impossible to have frames or these sequences generated by smooth vectors at this critical density. But the problem for more general nilpotent Lie groups is still open. But I think everyone suspects that it shouldn't be possible still.
Okay, thank you.
Thanks.
Is there any other question or comment? Okay, if not, we thanks again to the speaker.